Now, as promised, I told you that I would do a demo with molecular shapes, and so I'm going to do that. And to go along with this demo, there's a sheet that I have posted, and it looks like this. And it's sort of a summary sheet, and it's two-sided. It is posted on Blackboard. But so the first shape that we have are when we have a molecule that has 2 electron groups. And so you can actually build your own set of models. There's no need to go and order an expensive set of models off of the internet or from a store, when you can use toothpicks and marshmallows. Now mine are a little bit sticky, but they're still going to work. So the first thing that happens is, remember, we want our molecule to be, our electrons want to be as far apart as possible. So that is the principle of VSEPR theory. Molecules as far apart as the electron groups, as far apart as they can. So first thing we're going to have is we're always going to have a central atom. And so this is our central atom, and if it has 2 electron groups, so it's going to have 2 bonds, and we want these to be as far away from each other as possible. So again, set costs you maybe $3. So here you go. Linear. Central atom, 2 electron groups, as far apart as they can be. This is linear. This bond angle would be 180 degrees. Now, going into polarity, if these bonds are polar, if I switch it and move it around, can you tell which one, like, does this molecule have a top and a bottom? Could you tell there's a top and a bottom to this molecule? Ignore the fact there's a sticky part, but no, you couldn't. So if these are polar bonds, it doesn't matter. The molecule is still nonpolar because they cancel out. Now let's also talk about what kind of hybridization that would happen here. So we have single bonds. So this molecule has, the central molecule is sharing one S, which has 2 electrons, one S, and then one P. So we need, in order to form bonds, we need each of our boxes to have 1 electron. So we need to form 2 bonds, so we need 1 S box and 1 P box. So we get 2 orbitals, and we use 1 S and 1 P. So these are sp hybrid orbitals that form two bonds around here. So sp hybridization, linear molecule. All right. Next, when you have 3 electron groups, you have your central molecule, and then you have 3 groups that are on it. Now, 2 and 3. All right, so now let's stick our bonds here. All right, so now this is, we want our electrons as far apart as possible. That's how we get it. This is trigonal planar, because you see how they're all in the same plane. So trigonal planar just makes a big triangle. So if you were to connect the dots, it would be a triangle. So this is a 120-degree bond angle. And now you can also see how, if these are all polar bonds, there's no way that you could tell where the top of the molecule is. Like you can't tell. It's not distinguishable. So let's also talk about hybridization. So here there are 1, 2, 3 bonds, or 3 groups. So 3 electron groups. So this molecule needs, so 1, 2, 3. So 1s, 2p, so sp2. So it forms 3 sp2 hybrid orbitals. Now, once we get to 3 electron groups, we could start having lone pairs. So the way that I do this, so this is electron geometry, and this is also molecular shape if you don't have lone pairs. So this would be one central atom, A, X, 3, E0, or just AX3, no electron groups, or no lone pairs. Now, if we have one central molecule, two bonds, and one lone pair, so the lone pair exists in the electron geometry, but remember, electrons are very small. We cannot actually see them. So the molecule that we see looks like this. So this is bent. So this represents one central molecule, A, X2, E1. So there's a lone pair that's gone now. Lone pair's gone. So this is bent. And again, it would still have, because the lone pair counts as electron groups, this would be sp2 hybrid orbitals. So 3 electron groups, you can have trigonal planar electron geometry, and you can have trigonal planar molecular geometry, or you can have bent geometry. All right, let's move to our next one. 4 groups. Now, most of the time, we have our central atom, and I know if you already watched the lecture video, you already know what's going to happen, but we're all going to say, my fingers are getting very sticky, but that's okay. So it makes it fun. Science is fun. And yes, this is something, you can try this at home. So most everybody's going to say, this is as far apart as they can get. And then we start sticking our groups on the end there. Sticky, sticky, sticky. Don't let your marshmallows get too hot. That's the moral of the story. Okay, so you're going to say, well, 90 degrees is as far apart as they can get. Well, that's not true. If you orient this in a 3D shape, so you kind of turn it like this. So now, look at this, it's a pyramid. So if you were to fill in, you know, the lines and the gaps and make an actual 3D molecule out of this, all these angles would be the same. Again, this is, it's just kind of pretend, it's a visual. Then all of this, it's a tetrahedral geometry is what this is. Now, with tetrahedral geometry, you have 4 groups. So on here, you have 1s and 3p orbitals that hybridize to form 4, 1, 2, 3, 4, sp3 hybrid orbitals. Now, in a tetrahedral molecule, if these are all polar bonds, it can be nonpolar. They will all cancel out because all of these bond angles are the same. So if all of the bonds are nonpolar, you wouldn't, well, if it's nonpolar, then it's a nonpolar molecule. If they're all polar, though, they're still going to cancel each other out. You would not be able to tell where the top is and the bottom. Now, let's start talking about lone pairs here. So when we have 4 electron groups, we have tetrahedral electron geometry no matter what. Now, if we have no lone pairs, so AX4, so 1 central molecule for A, X4, 4 bonding. That would be tetrahedral shape. Now, if we have 1 lone pair, still the same tetrahedral geometry, but the shape is a pyramid. So it's a pyramid with a triangle base. So this is why we call it Trigonal Pyramidal. So look, it's 3D. And it sits like this. Now, could you tell where the top of the molecule is here? Yes, you can. Yes. Because the pyramid doesn't extend this way. Whoa, that looks way different, doesn't it, when I turn it around? Yeah, so if it's trigonal pyramidal, this is a polar molecule. Because here's your lone pair. And so I like to think of lone pairs as kind of the top of the molecule. Now, so this would represent 1 central molecule, A, 3 bonding groups, so AX3, 1 lone pair, E1. So AX3, E1. Trigonal pyramidal. Now, we can also have 2 lone pairs. So when we have 2 lone pairs, just take off another one. Okay? So now it looks like this. Does this look familiar? Yeah? Does it look like this one? where I take a group off. Look, it does! It's the same shape, bent. It's also bent. So this represents, now when you're looking at this 3D with these models and you can't see the electron groups, you're going to go, oh, well, it's the same. Yes, it looks the same. That's true. But this one has 2 lone pairs. So this is an A, X2, E2, because here were your lone pairs. So again, a bent molecule is polar because you can clearly see no matter which way you turn it, there's a top and a bottom. So that's tetrahedral. So tetrahedral geometry, if you have 1 lone pair, it is trigonal pyramidal. If you have 2 lone pairs, it's bent. All right, move on. Now it's going to get even more fun. Flip the page over if you're following along. 5 electron groups. So it's a little tricky to build this molecule, and I'm going to get super sticky. But that's the fun part. All right, so you have a central molecule here. Now, we have 5. So the first thing we need to do is we need to arrange like we did with Trigonal Planar. So here we have our 3 groups. Let's go ahead and stick ours on there. Okay, so here we have our 3 groups. They're all in the same plane. These are called equatorial. Equatorial. Now we got to put 2 more on top, or well, 2 more on the molecule, on our central atom. So we're going to put 1 on the top and then we're going to put 1 on the bottom. Again here. Okay, so we got, I'm going to hold these out. Okay, so it looks like this. You have 3 that are in the same plane, and then you have 2 that are sticking up and down. Now, we call this is Trigonal Bi-Pyramidal, because do you see how this is a pyramid with a triangle base, as is this side of it. It's a pyramid with a triangle base. Again, it's kind of hard to see. There you go. Now, these 3 that are in the same plane, we call these equatorial, and then these that are up and down, we call them axial. So these are axial and equatorial. Now, our bond angles, just if you're interested, are on our equatorial, because again, we want these to be as far apart as possible. There, so this is a trigonal planar, so they are 120 degrees apart. Now, our axial ones, they're only 90 degrees. Now, so this is Trigonal Bi-Pyramidal. This represents an AX5 or an AX5E0, so no lone pairs. Or an electron geometry is always Trigonal Bi-Pyramidal when you have 5 electron groups. The hybridization here, we have 1, 2, 3, 4, 5. So we have 1s, 3 p's, 1 d. So you have 5 orbitals, sp3d1 or sp3d. So those are your hybrid orbitals there. Now this one, if these are all polar bonds, they will all cancel out. Now, if one of them is polar and the other are not, just think, can I find the top of a molecule here? Now, when we start taking off electron groups for lone pairs, remember, we want them to be as far apart as possible. So the first one we take off is an axial. So you take off an axial. Okay, so this represents AX4, 1, 2, 3, 4, AX4, E1. And what does it look like? It looks like a seesaw. So look, see, it's a seesaw. So there you go. It is a seesaw molecule. Now, next, we take off another lone pair. So this is AX3, E2. And what does this look like? It looks like a T. So it's T-shaped. Now, when you have 5 electron groups, you can also have 3 lone pairs. So when you take off your third lone pair, here it is. Linear. So this is AX2E3. So 2 bonding groups, 3 lone pairs, 1, 2, 3. So they can be here. So this is the as far down as you can go on a 5 electron group. So this is 2 bonds, 3 lone pairs, linear. Now, let's have even more fun with it. We know if we have 6 electron groups, we have our central atom, and then we're going to have 4. And I'm going to get super sticky on this too, and that's okay. 2, 3, 4. All right, so now, when you do this, you get an octahedral molecule. So that means that you have 4 in the middle, no matter which way you turn it, you have 4 that make a square, and then you have 2 that kind of go up and down, no matter which way you turn it. So if all of these are polar bonds, this would be a non-polar molecule. So now let's see what happens when we start making lone pairs. I know, again, by the time I get to this point, my marshmallows are usually still pretty sticky and falling apart. Okay, so when we have, so this represents AX6, because there's 6 electron groups on here, and theoretically they're all at 90-degree angles. So let's start taking these off. So here I've taken one of them off. So that leaves me with 4 that are sitting like a square and 1 that's sticking up. So this makes a pyramid. So this is a pyramid with a square base. Again, you may have to use your imagination. Okay, so it's a square base. So that we call this square pyramidal. This is polar. You can always find the top. Even if all the bonds are polar, the molecule is still polar. Plus, there are lone pairs, so you can always find the lone pair. So the lone pair would actually be going down where the bottom of my hand is. So this represents AX5, so A, 1, 2, 3, 4, 5, AX5, E1, which would be this one down here. Now, if you have 2 electron groups, 2 lone pairs missing, so where you would have AX4E2, all you have left is the square that's in my hand. So this is square planar. Now, I did not yet talk about hybridization here for our 6 electron group molecule. So let's do that real quick. So here we have 6 electron groups. So we have 1 from the S, because there's 1 S box, 3 from the P, that gives us 4, so sp3, and then we need 2 more. So we borrow from the D orbitals, so we need 2 of those. So sp3d2, total of 6. There. Now, going back, when we get our 2 lone pairs, this one, if they're all polar bonds, would you be able to differentiate the top from the bottom? Oh, so a square planar can be nonpolar, because in this case the lone pairs cancel each other out because they're in the front and the back. So hopefully that made things a little bit more fun. If you want to demonstrate with polarity, get yourself something like raisins, and here I have some fruit snacks. So here, if I have a tetrahedral and you can use that you can use this to represent a lone pair, or you can use it to represent like a different atom. Could you always find where the red one is? Which one's the red one? That's the top of the molecule. Look at that. So this would be a polar molecule, because you can find the top of it. Say, oh, there's the top, there's the top. You can always identify the top. So have fun. Find some stuff that you can poke toothpicks in. Make models. Try this out. Get your hands on it. It's the best way to learn it. So, you know, talk to it. Talk yourself through it. Use the sheet. It tends to make a little bit more sense.